Hey Tyler.
Hello Dakotas, how are you?
Good. Welcome to the post-class video on electrochemical cells. And so here I've drawn up a really beautiful drawing of an electrochemical cell. And I just wanted to review the parts of the cell. And so, of course, we have the two chambers that contain the two different half reactions. And in this one I have a mixture of iron 3 plus and iron 2 plus. And over here we have nickel 2 plus. And then we have the electrodes sticking in that are going to connect to the circuit, right? And so over here we got the nickel solid. That's a metal, nickel metal electrode. But over here I have an electrode that's labeled C solid, carbon. Turns out you can make electrodes out of graphite. And when you make electrodes out of graphite, you only do that when you want the electrode to be inert. The electrode's going to deliver electrons or accept electrons, but it's not going to actually participate in any reaction.
Right, and the nickel will.
That will, exactly. The electrodes are connected through a circuit, and this is where the electrons are going to move through the circuit, and this little thing represents a voltmeter. Usually you want to measure a voltage or a current or something like that. But of course, if you know anything about circuits, you have to have a complete circuit. You have to have a loop, right? And so, what's this thing called?
Well, that looks like a salt bridge.
Salt bridge. And I've put little Na plus and NO3 minuses in there all through. And salt bridges, you can make them a bunch of different ways. In the lab, all you do is you take a little short piece of rope and soak it in a solution of sodium nitrate or potassium nitrate so that it's saturated with those things, and then you drape it across your two containers. And the idea is that as electrons flow through here, you need to kind of make sure that the charges are balanced, right? Negative charges is going through the circuit, and so the salt bridge allows ions to move so that maybe if electrons are moving that way, you have negative charge. You need to balance that by having positive charges, i.e. the sodium ions, moving through the salt bridge. Right? The key is that they have to be kind of inert, basically spectator ions in the salt bridge.
And we know that these guys are very good spectator ions.
Exactly. A fancy way to make this, and this is actually the way we used to make these, is to fill a glass tube with basically Jello. But instead of using,
actual Jello,
you use scientific Jello, and the solution that you make the Jello with has the salts in it, so they're kind of trapped in there, but they don't move really quickly. Okay.
So now we're super high tech and we just use wet rope.
Exactly, wet rope. Okay. Well, one of the questions is, which of these is the anode and which of these is the cathode? What do you think?
Hard to know.
Hard to know. It's hard to know. And different things are going to tell you whether something's an anode or a cathode. Right? So for example, if I say that this electrode over here is positively charged, we know that that's the cathode.
Right. Cats.
Cat. C-A-T. Well, cat has a plus sign.
Right.
And so that would tell us that that's a cathode.
Right.
And that would also tell us that reduction happens there.
Red cat.
Red cat.
Got it.
Another way that we could tell is if we knew which direction electrons were flowing in the circuit.
Right.
Right? So if electrons are flowing in the circuit that direction, which makes sense if that's positive, if that's the only thing we'd know, we would know that electrons go towards the electrode where reduction happens. Reductions consume electrons.
Right.
Right? So if electrons are going through the circuit towards electrode, that means that reduction has to be happening there because there are excess electrons going there that get consumed. Right? Where are they going? They're going to the reduction.
Right.
Well, let's all go to the reduction. What else?
If we knew what the half reactions were? Or what direction half reactions are happening in?
Yeah, so we could have been given a balanced equation.
Right.
For example, I could have said that the reaction that happens here is that Fe3 plus reacts with nickel to form Fe2 plus nickel 2 plus.
Right. And we can actually look at these ions and say, hey, the iron's getting reduced.
And the nickel is getting oxidized.
So then we would know what's happening in each of these halves.
Exactly. Just for completeness, I would have to put a 2 there and a 2 there to make sure that everything's all balanced. And also aqueous, solid, aqueous, aqueous.
Mm-hmm.
Okay, right, so if I was given that information, I could tell also the iron is being reduced. That happens at the cathode, it's positively charged. So another way is, maybe we don't know which direction this reaction goes in.
Right, question mark.
Question mark. But maybe you know that the nickel electrode is getting smaller. Like
Right.
you weigh it before you set this up, you run this cell for a while, then you weigh it again, you find that, oh, the mass of that is decreasing.
Right.
Well, what does that mean? That means that the nickel solid is dissolving.
Right, and it's becoming this nickel ion.
Exactly. And so that means that the nickel solid is getting converted to nickel 2 plus.
Which means that it's getting oxidized, so you know what's happening in this half, right?
Exactly.
Right.
Okay. What if you're not given any of that information? Who knows? Well, if you have a table of reduction potentials, you can look up the reduction potentials of both of these systems and figure out which one is more likely to be reduced. Is it more likely that the iron 3 plus is going to be reduced to 2 plus, or nickel 2 plus is going to be reduced to nickel solid? Right? And so you write out the half reactions and then ask the question, which one's more likely to happen? So I looked up these redox potentials, and you have to make sure that you have both the reactant and product correctly. Right? I can probably find a redox potential for iron 3 plus going to iron metal.
Right.
I can also find iron 2 plus going to iron metal, but the one I want is the one with both species that are involved in that actual cell, and so I looked up the iron 3 going to iron 2. And it has a reduction potential of 0.77 volts. The nickel, I think there's only one in the table that I have, nickel 2 plus going to nickel solid, has a potential of negative 0.5257 volts. So we look at these, which one's more likely to happen?
Well, the positive number.
The more positive number, right?
Right.
So that, comparing these, that tells us that this is going to happen at the cathode, that's going to be the reduction.
There you go.
That means that this one, we can't have two reductions, right? So this one's going to be flipped backwards.
Right.
And then also, we see that there's 1 electron, 2 electrons, so when we add these two together, I better multiply this reaction by 2.
Right.
Now the cool thing about voltages is that when I multiply the equation by 2, I don't multiply the voltage by 2. Right? So the question now becomes, well, what's the voltage for the whole cell?
Right, what are we going to see at this voltmeter here?
Right. And the answer is you take the reduction potential at the cathode minus the reduction potential at the anode. Even though an oxidation has happened there, you minus the reduction potential.
Oh.
Right? And that's why there's a minus sign there, is because you're flipping the reaction backwards. Right? But bottom line is you look up the values in the table, and it's the cathode minus the anode, or the reduction minus the oxidation. And so when I do that, I take 0.77 minus negative 0.257, and we get da-da-da-da, da-da-da-da. So we get an E cell, 1.027 volts. So I think that covers all the material we looked at in class. There are a bunch more examples where you have to do this last piece. And again, practice makes perfect. And so try to complete the activity and then practice a few more problems from the textbook.
All right, good luck.
Great, good luck.